Hello there, Mr. Sutton here, bringing you the Algebra 2 9-1 lesson on using normal distributions. In this one, we will be finding probabilities in normal distributions and standard normal distributions. Since this is our first lesson on statistics, we're going to start this off with a review of some important statistical terms because we're going to be using these later on, and it's helpful to know what we're talking about. So the first three we're going to talk about are what we call measures of central tendency. These are ways of figuring out kind of where your data is clustered. One of these that you're probably familiar with is called the mean. This is the symbol for this is this weird little U shape here, which is the Greek symbol for mu. We're going to be using that quite a bit. And the mean, just to review, is the average value of the data, which is to say if you take the sum of the data and divide that by the number of data items, this will give you the average or the mean. And this is the main measure that we're going to be using throughout this lesson, even though we're never actually going to calculate it directly like I show here. Now, another way of measuring central tendency is something called the median, which is the middle value when you put your data in order. Now, the mean and the median could be the same number, or they could be different if your data is skewed to one direction or the other. We'll talk about that a little bit more toward the end of this lesson. Now, the final measure of central tendency that we use often is called the mode, and this is just the most common value. We won't use this one a whole lot here, but it is an important one to keep in mind because it's especially helpful when your data values are not numerical, but you can still talk about which one appears the most. Now, there's another way of talking about central tendency and talking about how close things are specifically to the mean, and this is the standard deviation. Now, standard deviation, there's a special symbol for that one, this little weird O with a tail at the top called sigma. That's another Greek letter. This is lowercase sigma in case you're used to that uppercase E looking thing. And this is talking about how much a typical value differs from the mean, or just basically to put it this way, how spread out your data is. So if you have a low standard deviation, then that means your data is not that spread out, so most of your data is clustered near the mean or the average. If you have a high standard deviation, then that means your data is kind of all over the place. Now, we're not going to calculate standard deviation directly in this lesson. We're just going to be given this and the mean, and we're going to use them in other ways. But just to review how this is calculated, because it's good to know where this comes from, we basically take each of the data items and we're going to subtract the mean from each data item, and we're going to square that difference. So we do data item 1 minus the mean, square that. We do that for data item 2 minus the mean and square that. And we take all these squares of differences from the average and add all of these things together. Then whatever sum of these differences we get, we take the average of that sum using the number of data items. When we do this, we end up with something called the variance. The variance, if you take the square root of the variance, that's what ends up giving you the standard deviation. So this is how you could actually calculate it by hand if you needed to. But in any case, it's important to know that we are getting this by using the mean of the data. Now that we have that little background on some statistical terms, let's talk about normal distributions. Now, a probability distribution in general, and you saw this if you took the honors version of the course in the last chapter, it's basically a graph of what all the frequencies look like if you put them all together. Now, a normal distribution is data whose frequency follows what we call a normal curve. And that doesn't sound like a very helpful definition, so let's get a little more specific on what a normal curve looks like. A normal curve is a specific symmetric bell-shaped curve, such as the one in this picture below. And when I say it's a specific bell-shaped curve, it is this curve. This is the normal curve. And the areas under each region of this normal curve are always going to be the same. For example, this region here is always going to be 34%. This little tail over here is going to be 0.15%. So what does this all actually mean? You might notice down here below the curve, we've got these labels on these different region sort of boundary points. Here's mu, that is the average of your data. And this little sigma here, remember that was your standard deviation. So this little region here is one standard deviation to the right from the mean. This over here is two standard deviations to the right. This one over here is three standard deviations to the left. So we've got this all mapped out, and we know exactly how much of this curve is contained depending on how many standard deviations you move away from the center. So because we are symmetric here and it's 34 on each side, that means there is 68% of your area within one standard deviation of the mean. And moving out a little further, 13.5 and 13.5, that's an extra 27% you're picking up. So that's 95% of your area is within two standard deviations. So the vast majority of your data is just two standard deviations away if you've got a normal curve, a normal distribution. So this would be pretty good information to know whether or not you have one of these distributions. It really tells you a lot about where your data is clustered. And just going a little bit further, this extra 2.35%, that's a grand total of what, like 4.7 more? So that would be 99.7% is within three standard deviations. So you know if I'm telling you that this data is more than three standard deviations away, then that is really well outside kind of the common type of data you're getting in this distribution. Now, why do we care about the area under the curve? Well, when we want to find the probability that a random x value is within a certain range here, what we're basically asking, in a normal distribution, your probability of a random x being between a and b, we're just asking for the area under this normal curve. So when we ask for probability, we're just asking for this area. So let's do a quick example involving this type of probability reasoning. We're told a normal distribution has a mean of mu and a standard deviation of sigma. So they're just giving us kind of a general situation here. They haven't defined real specific numbers for those. And they're telling us that an x value is randomly selected from the distribution. Find the probability that our x value is between mu minus 2 sigma and mu. So basic idea here is you've got your normal curve. You just have to add up the area under the normal curve between the values that they've given you. So take a look at that normal curve and add up those values and let's see what you get. All right, so here's our normal curve again. It's up to you whether you want to redraw this fresh or just use the one that you saw earlier in your handout. But if we're going from mu minus 2 sigma to mu, that's from right here to here. So I'm just going to shade that in so you can see what we're dealing with. And we're just adding these two areas together. So that's going to be 13.5 or 0.135 if we turn that into a decimal, plus this would be 0.34. And then just adding those together, let's see what we get. And I'll do this on my calculator just to make sure I don't mess this up here. I'm having a little humility. So we have 0.135 plus 0.34. And that comes out to 0.475. So that means there's a 47.5% chance that this x value falls within this given region. For this next one, they're telling us that a normal distribution has a mean of 33 and a standard deviation of 4. So now we're getting specific. They want us to find the probability a random x value from this distribution is between 33 and 45. So a good way to start this would be to draw a normal curve and leave out the stuff underneath because we're going to relabel things. We're going to use the mean and the standard deviation they gave us here to assign values for what we were previously calling mu, mu plus sigma, and all those other ones down there. Once we've got kind of our own specific normal curve for this situation written out, at that point, we'll just find the area between the values that they gave us. So just to start things off here, go ahead and draw out your normal curve. And feel free to add in these percentage numbers. It's always going to be the same percentages, so although these are kind of weird to deal with, at least it's going to be the same every single time. This is very standardized. Now let's get our values down here, or at least we'll start the process. They told us that we had a mean of 33, so that's always the dead center one. That's our mu right there. Standard deviation of 4 is telling me how much I have to add or subtract for every line I move to the right here. So mu plus sigma in this case is really just 33 plus 4, or 37. And we can use the same reasoning to get the rest of these. So this is a pretty good head start. Pause the video, see if you can finish this labeling here, and then find the values that they're asking for. Alright, so going a few more in this direction, 37 and a 4 gives us 41, then we've got a 45 here. Going back to my mean and now subtracting the standard deviation each time, we've got 29, 25, and then 25 minus another 4 gives us 21. Now we wanted the area between 33 and 45, so that's from here all the way to here. And just looking at what areas that actually involves, we've got 34%, 13.5%, so we'll add these up. And it's up to you each time whether you want to go percentages or decimals. It won't really matter for the end. I guess it'll matter if it's multiple choice. Just pick whichever one the answer choices are. And then we also had this 2.35% that we're going to add on there as well. So let's add all these together. So 34 plus 13.5 plus 2.35 comes out to 49.85%. So all this normal distribution bell curve stuff is kind of neat, but where would we use this in a real-life setting? So here's one possibility. Let's say that the scores for a state's peace officer standards and training test are normally distributed with a mean of 55 and a standard deviation of 12. And then the test scores range from 0 to 100. They would like to know, as a part of this problem, about what percent of the people taking the test have scores between 43 and 67. So if you know about normal distributions, you can very quickly figure out this kind of information, even if you don't actually have all of the scores in front of you, which is kind of important because this might be, tens of thousands of different scores that are being taken into account. So with all that said, pause the video and see if you can figure out what percentage of the people actually do have these scores. And then once you're done with that, feel free to try part B, where we have an agency only hiring applicants with scores of 67 or greater. What percentage of people fall into that category? Give both of these a shot. Alright, so to do either of these, we need to make our own normal curve again, using the mean and the standard deviation from the problem. So here is my normal curve. I'll redraw it. And now let me label this here. Mean was 55, so that's our mu. Our sigma in this case is 12, so we've got 55 plus 12, 67. And then we've got 79 and 91. And then going the other direction from 55, we've got 43, 31, and finally this would be 19. So if we want scores between 43 and 67, 43 to 67 is right here in this middle area. So that's just going to be 34% plus 34%, which I don't need a calculator for. That is 68%. And yes, it is awfully convenient that they asked for exactly 43 and 67. You might be wondering, what if we're not so lucky that they ask us for things that are exactly one standard deviation in one direction or another? Well, we'll deal with that later. But for now, let's just be grateful. For this next part now, they wanted scores that are 67 or greater. So that's going to be everything from 67 onward over here. So that's going to be 13.5% plus 2.35 plus 0.15%. And let's plug that into the calculator. So 13.5 plus 2.35 plus 0.15 comes out to exactly 16%. So 16% apparently of people actually are eligible for this agency. So pretty selective, it sounds like. So just to circle back with a thought some of you might have had earlier, how could we figure out probabilities for normal distributions where we're not dealing with numbers that are exactly on the border between those standard deviation regions? So for this, we're going to use something called the standard normal distribution. The standard normal distribution is just a normal distribution, but it's a specific one. It's one that has a mu, an average of 0, and a sigma, a standard deviation of 1. So here's a picture of that critter right there. That's our standard normal distribution. Average is 0, standard deviation of 1. And you might be wondering, well, how does this help us? Very few real-life situations are going to have this sort of distribution. The way it's going to help us is we're going to calculate something called a z-score. You might have noticed these have all these little z's down here. So the z-score is essentially how many standard deviations an x value is from the mean, and this is for any mean and standard deviation. We're going to take any mean and standard deviation and we're going to calculate a z-score for whatever x value you're dealing with, and that'll sort of kind of scale it down to this much nicer looking normal distribution. So how do we get this z-score? So our z-score is going to equal, we're going to take the x value that you're starting with and subtract the mean from it, so x minus mu, and then we're going to divide that by sigma. So this basically figures out like how far away you are and scales it back to this 0, 1 kind of setup. Now, how do we actually use this z-score to figure out the area under this curve? So there's a couple ways you could do it. There are tables out there that if you have the z-score, you might be able to find the z value in the table, and then that would give you the percentage. There's also technology, namely Desmos. On the Desmos grapher, for example, this little weird function here will tell you the probability of all of the area less than or equal to your z-score. And we'll go into using this a few times, but just to kind of break down what this is doing, normal dist is normal distribution. 0 to 1 is telling us that we want this standard normal distribution. 0 is the mean, 1 is the standard deviation, so that's where those numbers are coming from. And this .cdf is just telling you kind of what to do with the normal distribution, basically telling you you want this area percentage under it. And z is just the z-score that you enter in there. Now it is important to note, some of you might have noticed that we get the probability of x less than or equal to z. This is giving you the area to the left of the z-score. It always gives you the area to the left, and this is also how tables with these different values are set up. So you might wonder, well, that's great if I just want the area to the left of some z-score, but what if I want the area to the right? This doesn't give you that value. However, the good news is if you want something to the right of a z-score, since all of this probabilistic area here adds up to 1, because probability, the most you can do is 100%, so all the chances add up to 100%. Since it all adds up to 1, you can just do 1 minus your original z-score probability. 1 minus the probability of x less than or equal to z. And that gives you this greater than area. Now what if you want the area between two values? That was like one of the first problems we did. If you want the area between two z-scores, then you need to take the area of the greater z-score, let's say 2, and you need to subtract the area to the left of the lower one. So if you take the greater and subtract the area of the lower, you get the in-between area left over. So that's how to handle some of those weird cases. So we're going to give this z-score thing a little test drive using a real-life problem. So we have a study that finds the weights of infants at birth are normally distributed with a mean of 3270 grams and a standard deviation of 600 grams. We want to use technology, namely Desmos, to figure out the probability that a randomly chosen infant weighs one of the following things. So we're going to do part A, less than 2,800 grams together. I'll show you the ropes on Desmos, and then you can try out B and C on your own. So first off, let's get a z-score, because whether you want to know if something is less or more than a certain value, you need a z-score to kind of anchor things. So again, that formula was going to be x minus mu over sigma. So in this case, we've got 2800, that's the x value, minus the mean, which was 3270, all over sigma, which they said was 600. And let's go to Desmos to figure this out. So I'm going to figure everything out on the graphing version of Desmos because the normal distribution function I'm going to use requires this version of Desmos. The scientific version actually doesn't have that capability. So just keep that in mind. So let's do, let's see, fraction 2800 minus 3270 all over sigma of 600. And that comes out to about negative 0.783. All right, so what we're going to do now is actually plug this into that normal distribution function. So let me go back to Desmos, and I'll just make a new window here, a new entry. I'm going to do normal dist, D-I-S-T, and then I open a parentheses, and I'm going to put in the default mean and standard deviation in here. So the first number is the mean, the second after that comma is the standard deviation. And you might have the idea that you could put any mean and standard deviation in here, and you actually could, but we're going to use this z-scored method as one way of doing this. So now after you wrote that out, you have to do a dot, a period, and enter CDF. And then a parentheses after that, you're going to put in your z-score, which is this value up here, negative 0.783, and we'll just use the rounded off version of this. So that gives us an output of 0.217. So this is actually the area to the left of this z-score on the standard normal distribution. So we got 0.217, so roughly 21.7% of infants are going to be less than 2,800 grams. All right, so with that technology in mind, pause the video and see if you can figure out part B, how many are going to be more than 3,800 grams, and part C, what percentage are falling between 2,800 and 3,800 grams. All right, so for part B, in order to deal with 3,800, I need to generate a new z-score. So there's my formula again. This time I'm going to do 3,800 minus 3,270 over 600. And let me go back into Desmos, and I'm just going to sort of mooch off of my first entry here. I'm going to change this 2,800 to a 3,800, because why reinvent the wheel? That comes out to 0.883. And now I will plug that in to get a value. So I'm going to go back into my CDF function here, and I'm going to make this 0.883. I do have to be careful though, because this value that it's giving me right here, this is actually all the stuff to the left of 3,800 grams. If I want the stuff to the right, then I need to take the complement of this and subtract this from 1. So the way I've written it out here is I actually need to do 1 minus the probability of x less than or equal to 3,800, which is what I just found. And to actually do that here, I can just really quickly go to the beginning of this normal dist entry I did and put a 1 minus all that in there, and I get the complement of 0.189. So about 18.9% of infants are going to be more than 3,800 grams. And now for part C, to find the percentage between 28 and 3,800, basic idea here is I need to figure out the percent that are to the left of 3,800 and subtract the percent that are to the left of 2,800. And I've already kind of got all those values. So this is my setup for what I'm going to do on Desmos. So let me take a percentage to the left of 3,800, and I can get that by just getting rid of that minus 1 in front of that normal diff. Now I get my 0.811 back. And I'm going to take that, and I'm going to copy and paste all of that. And I'm going to move to the right of it, and I'm going to subtract now the same function But instead of just a complete repeat, I'm going to put in my z-score for this 2800 business, which, just to review that was this negative 0.783. So I'll replace this with negative 0.783, and that difference gives me about 0.595. So about 59.5% of babies fall in this range for weight. Now, one thing that is worth pointing out is you might be wondering again, this 0, 1, do I have to do that every time? Z-scores, they're really helpful. They give you a rough idea of how many standard deviations away from the mean any x value is, and it's really useful for comparing x values. But if you're using Desmos, there is actually a way to sidestep this whole z-score process. If you do normal distribution, and instead of doing 0, 1, you put in the actual mean and standard deviation from the problem. So 3270, 600. And then you do the same thing as before, .cdf. This time, if you just plug in the original value, for example, in this case 2800, it will give you the exact same value that whole z-score process got you. So if you're just finding one value, this is a good shortcut, but it is still important to know how to find z-scores, because sometimes you might not be able to use Desmos. If you're stuck with using a table, for example, then you would have to calculate the z-score by hand and compare it to the table. So it's good to know. Everything that we've been doing in this lesson kind of assumes that we have a normal distribution. So here's a look at that again. It's that nice bell-shaped curve. And an important point to kind of note here is that in a normal distribution, a perfect normal distribution, the mean and the median actually will equal each other. That's what gives it this symmetry in this sort of distribution here. Now, this isn't the only type of distribution out there. There's a few other ones where the mean and the median don't equal each other. For example, in a skewed left distribution, like this one here, the mean is actually less than the median. And in a skewed right distribution, like this one shown here, the mean is greater than the median. So this whole left versus right thing is basically where the mean is with respect to the median. Now, if your mean is to the left of the median, that means you've got some really low values sort of bringing the mean down without really affecting the median. So you end up with this tail on the left side. If you have a mean that's higher than the median, that means you've got this tail on the right side sort of dragging things up. So if you're trying to figure out numerically whether something is skewed left or right, and you have the mean and the median, you just have to compare them. But visually, you just have to note that your skewed distribution is going to have a tail in the direction of the skew. So skewed left has a left tail, skewed right has a right tail. So our last little segment example here is we're just going to be determining whether each of these histograms with some data in them has a normal distribution. And again, the reason that we care about this, and it's an important question to answer, is if something has a normal distribution, that means I can use all of that math basically that I used earlier in this lesson to predict where values are going to fall on that curve. If something doesn't have a normal distribution, then using all that z-score stuff and everything else is not going to necessarily give me an accurate answer. So pause the video and see if you can figure out which of these has a normal distribution. All right, so for our first one, this is a relatively bell-shaped curve. I mean, it's not a perfect bell shape, but it's going to have to be close enough for a real-life problem. So we would say this is a relatively normal distribution. For this other one here, we are definitely not bell-shaped. We have a little tail going over to the right here, so this is skewed right. And since it's skewed, that means it's not going to be a normal distribution. So that's it for this one. Hopefully, if you came into this lesson with a skewed perception of what was normal, we've fixed that. Until next time, Mr. Sutton signing off. I'll see you later.